Today we're going to be looking at section 6.1, polynomial functions and polynomial inequalities. Here we're in the learn section, and these are our objectives. We want to determine whether given values are solutions of polynomial equations. We want to graph factored polynomials, solve polynomial equations, solve polynomial inequalities, the behavior of polynomial as x goes positive or negative infinity, and then use polynomial inequalities to solve applications. So we're going to go through the learn. So here is a little information about what polynomials are. It is very important that you understand degree. So you'll have either a number and a variable raised to a power, or it could just be a number and a variable with no power, or just any number. All of those terms being added, subtracted, or multiplied together make polynomials. So you won't see any square roots, which also fractional exponents. You won't see any variables in the denominator. So this is kind of like the generic what a polynomial look like. So zeros of a polynomial, they just use the number c to mark that. If you plug in that number c to the polynomial and you solve it, you should get 0. So those are the x-intercepts. Here's the definition of a polynomial again, and they're showing you that the degree is the largest exponent, so n, whatever that is, and then the leading coefficient is the number in front of that largest degree term, which we'll see a little bit more of that in practice and explain some subtle differences depending on what the polynomial, what form is in. All right, so here's some examples. So you have 6x squared minus x cubed, and then you have 12 plus 5x on the other side. This is equal. You would move everything to one side, and then the 3 being the largest exponent would be your degree. They want to know is x equals 4, 0. So you would plug that in. So this is what they're doing with example 1, and checking to see that both sides equal, and so it's a true statement. And then you can do that with the other examples as well. Finding zeros, you can see graphically. If it's a graph, you can see where it crosses the x-axis. You can also solve using the calculator method, and they kind of take you through the step-by-step to enter. So the one that I use may be a little bit different. This one is asking left bound and right bound. And you can kind of see it's making some lines. You're just going to trap the 0 between those two lines. So when you enter your equation and you graph it, and then you do the button pushing to get to the part that calculates the 0, you will be prompted to answer a few steps. It'll say left bound, which you will arrow your cursor to the left of that 0 and hit enter anywhere on the left. And then it'll say right bound, you arrow to the right and hit enter. And it's going to just trap. You're just telling the calculator where to look for the 0, because there's more than one. So it wants to know which one do you want, and then you do one at a time. So that's kind of the process that's happening here. And then graphing factor polynomials. So if a polynomial is in a factor form, it'll be a little bit different to graph it. These are some of the basic forms of polynomials. What x squared looks like, so any even degree, both endpoints will go in the same direction. Odd degree, they go in opposite direction. So here's that again. So we talk about the end behavior. We want to know what's happening as x gets really, really big in the positive, or we say really, really big in the negative, or really, really small. And this is how you write that. So if you have an even degree, so like 2, 4, 6, 8 is your biggest exponent, then your polynomial will go both ends in the same direction. If it is positive, that's the leading coefficient, then they're both going to go up. So this says as x goes to negative infinity, so that means as I'm going to the left side of my graph, the y value, p of x, is going toward infinity, positive infinity. And then this says as x goes to positive infinity, so as we're going to the right, also our y value is still going up. And then when n is odd and positive, then the right side is up, the left side is down. So that's what this is saying. As x goes to negative on the left side, then the y goes to negative infinity. And then as x goes to positive infinity on the right side, y goes to positive infinity. And then you have the same scenario when the leading term is negative. They go down and the directions change. So negative goes to positive and positive goes to negative. But when it's even, both ends either go negative or both ends go positive. So here's some more examples. And again, I'll just do all of these with you in Hawks and explain those. Now, let's look at this factored form. The factored form is nice because it allows you to find those zeros pretty easy. You would just set each of these terms equal to 0, and you can solve and figure out exactly where those zeros are. When it comes to the degree, you need to be mindful of property of exponents. Whenever you multiply, it's adding the coefficients, not adding the coefficients, adding the powers of x together. So you have 1x here, it's going to be multiplied, so x and x give you x squared, 2x, and then you have a third one. So when you multiply here, this is a third degree. As you can see, it's an odd graph, kind of what we saw on the previous page. When it's odd right here, it's going to, one end's up, one end's down. So when it's in factored form, counting the degree is counting the number of x's you have, even their powers. If it has a power, you add that as well. So, for example, this one, if you wanted to find the degree, it would be 1, 2, 3, because there's 3 x's here. This one is not in factored form. As you can tell, they're not in parentheses, butted up against each other, being multiplied. So this degree would just be 2, and as well as this one, its degree would just be 4. So finding the degree is different when it is in factored form. So just several examples. And then a few more examples here, another one. So then solving polynomial inequalities. Just depending on, they're just showing you all this. This is when we want to find out the y value is less than 0, less than or equal to 0, greater than 0, or greater than or equal to 0. Just showing you all 4 terms that we're going to be looking for. So here's a little video, and then let's talk about what this is asking and how we'll do this. This is saying you have this function. We want to know where is it less than 0. In other words, where is it negative? And you can see in the picture, they have shaded in red the intervals where this graph is negative. Now there's a method to solve it, but you describe it based on the x-axis. So this graph is negative from the far left, negative infinity, all the way till we get to the x value, looks like -3, and that's what that interval is. And then it goes positive for a little while, and then right here starting at -1, it is negative or below the x-axis until we get to +2. So that's that interval. And then you always do the union to connect separate parts. And also, depending on the inequality symbol, if you want strictly less than, then you will be using parentheses. If you want equality to be included, then you will use brackets. So this one wanted greater than or equal to 0. That is the positive parts. And I think they labeled that down here. And they show you that they put the endpoints in brackets because it's included equal to with the zeros. Let's got some more examples here. Talking about continuity and discontinuity of a function. If you have a break in the graph, then it's not a continuous graph. Continuous would be if it's all connected smooth line, and this is discontinuous function. This is the process that we're going to use to find those intervals when we're solving inequalities. And I will model this in Hawks when we start doing examples, but it first wants you to find the zeros, and then you're going to place the zeros on the number line, splitting the intervals into sections. Within each interval, we're going to select a test point, and you can pick any number, whatever is easy for you to work with. And then if the result is positive, then it's going to be positive for all the values in that interval. And if it's negative, then it's going to be negative for all results in that interval. And then we're going to write the solution set consisting of all intervals that satisfy the inequality, so depending on which one we're looking for. And again, I will model this when we start problem solving. And then I think we're getting toward the end. So here's the last page. This is an example. Now, when I do it, I kind of try to keep it simple. I may not actually find the numbers, but I will be able to figure out the sign, and we'll see. Just depends on what we have. And then here's just the rest of that example, just showing the solutions. And this is probably what I'll do, is be showing positive, negative, negative, something like this. And so what this is that they're going from this polynomial here, and they're multiplying these three terms together. So whenever they pick any number, so let's say if they're using the left side of this graph, and they can pick any number on the left of 2. So let's just say we pick -5, for example. If I plug a -5 here, this interval is going to come out negative, -5 plus 2. So that's why they're putting a negative here. If I plug a -5 here, -5 minus 1 is a -6. However, this parenthesis is squared, so it doesn't matter what you get here. When you square something, it is always positive, and that's why you're seeing a positive here. And then in the last interval, if I plug that same number, -5 here, -5 minus 3 is a -8, that interval is going to come out negative. And then at the end, when you multiply negative times a positive, it comes out negative, and then negative times a negative, it turns positive. This overall interval is positive. So no matter what number you pick over here, it's going to be positive, and that's what they're showing you at the bottom. So they've already picked some numbers, plugged them in, and these are the intervals that they've gotten. You wanted the intervals that were less than or equal to 0. So all the ones that are negative, less than 0 is negative, so you want from 2 to 1, and then all the way to 3. So I think you can just use one interval all connected from -2 to 3. You don't have to do that break in between there, only if you had to separate. So that's what they show down here. Solution set is -2 all the way to 3, because those are the two intervals that ended up negative. Okay, I think that's it. A lot of information here, but I will model this for you in Hawk. So let's jump over and start working.